So this morning or this afternoon, depending on where you are, I want to talk about the simple truth about complex impedance probes. And a lot of this kind of parallels some of the things that Frank and Marcus just mentioned, which was a really enjoyable presentation, by the way. I did enjoy it. And I do work in EMI simulation myself, so a lot of that was really interesting to me. What I want to talk about is what actually motivates us to measure impedance. I mean, there must be a reason that we're doing it. Frank and Marcus mentioned target impedance, and that's probably a popular one today, but there are a lot of other reasons also. I want to talk about what makes it difficult, what really is in the way of our measurements, and not only what's in the way of our measurements, but what's in the way of actually getting accurate measurements. Why do we use probes, and what is the role of the probe, and how does it influence the measurement, both in complexity and also in fidelity? I'll provide some tips, and unfortunately I don't have a live demo today, but we do have online demos that we recorded in case you'd like to see them. So the first thing is that impedance really isn't the end goal. Very few of us go measure impedance because we want to know what the impedance is, but it is a quantifiable metric that allows us to assess an end goal, and that is compliant performance. And so impedance is one of those things that relates to our compliant performance. And so the intermediary term is impedance, and we use it for that purpose. Of course, that's only not true if you're measuring target impedance, where our direct goal is for the purpose of measuring impedance. I have lots of papers on target impedance if you're interested, most of them about why it is that it's not really a good method of determining performance. In particular, the whole goal of target impedance only works if the impedance is flat, but if you have multiple resonances, then it doesn't work anymore. In any case, it is kind of a standard. We do 3D FEM extractions or 2.5D FEM extractions for the purpose of evaluating the performance of the board, just like Frank and Marcus showed. And this typically has a mask region, and that shows us what the impedance looks like as a function of frequency. And theoretically, at least, if you can stay below the mask, you'll be compliant. And again, of course, if you don't have a flat impedance, that may or may not be true. I think one of the best papers I've done personally on it would be DesignCon 2015, target impedance in rogue waves. If you can't find that online, you can let me know, and I'll be happy to share that with you. But the impedance does get into many different things, and along with target impedance, we're also interested in what the excess inductance is, what the ripple or noise are, and those are also influenced by this FEM impedance. Excess inductance is something that engineers struggle with a little bit because it's not really the same as inductance. And for example, if we took a 50 ohm coaxial cable and we terminated that into 50 ohms and then measured the impedance using a vector network analyzer, it would always be 50 ohms, it would be a flat impedance. And yet if we shorted the far end of the cable and measured it again, then it would look like an inductor, and eventually it would become resonant from the capacitance of the cable. And so when we talk about excess inductance, it's actually the part that's not equally absorbed by capacitance. And that's essentially what it is we're looking at when we look at board impedances. Step response also shows up in critical circuits, and that is really also a function of impedance. So here I'm showing the impedance of a DC power board. In this case, it's our standard VRTS3 demo board. And if we measure the LDO regulator with a ceramic capacitor, and we measure the impedance of the clock, you'll see that we see two different resonances. One at lower frequency, that's the stability of our regulator, and one at higher frequency, and that is a resonance from a skinny trace on the printed circuit board and a decoupling capacitor that's located at the reference clock. There are two reference clocks on the VRTS3 board. One is a 10 megahertz clock. The other one's a 125 megahertz clock. In particular here, we're looking at the 125 megahertz. And if you look at the scope screen, the top trace, that's actually the 125 megahertz. And if I stretch that out far enough, you'd actually be able to see the individual cycles. But this is a relatively long simulation. I'm using one of our J2111 current injectors, and it's connected directly into the 3.3 volt power plane that feeds the clock through one of the SMA connectors. Those two SMA connectors on the edge both connect to the 3.3 volt plane. And so in the middle pink trace, you can see that I'm just applying a current step to that 3.3 volt regulator. And in the bottom trace, that's actually the frequency of the reference clock versus time. It's a frequency versus time plot. That ringing is approximately 1 megahertz peak to peak, and that occurs at about 7 megahertz. And so the point of this really is that the impedance tells us a lot about a lot of different things. I said that it's an intermediary term for performance. And in this case, this would be phase noise or spurious responses. And so that 7 megahertz resonance interferes with the phase noise of the reference clock. And so one of the reasons that we want to measure the impedance is so we can look at things like how it interferes with that reference clock. A lot of us are familiar with step loads. In fact, most power electronics engineers are familiar with step loads, probably more so than measuring impedance. This particular step load is an interesting one. There's an article coming out, I believe this month or maybe early next month, about this particular measurement, which was done in conjunction with Qorvo. And this is one of Qorvo's power supplies for a high power pulsed RF power amplifier. They needed us to do a step load on their power supply in order to see if we could figure out what the performance of the power supply actually looked like. But it wasn't easy to do because we needed to do, first of all, a 3 amp step on a 65 volt power supply. So that's a pretty large step. The bandwidth of the step had to be up to 700 megahertz, which means that we couldn't use any cables. And so we needed to put it into a probe. And you can see this probe here that's just a little over 1 inch long. That's actually the step loader, and that's actually doing the, in this case, 50 volt 3 amp step. And I don't mention this for no reason at all, but we're going to come back to it because I think that there's this limitation in what we think of as a probe. We think of a probe as something that measures signals on a dot and transfers them to an instrument. In reality, that's not really true. A probe is a bidirectional communication between an instrument and a board. And in this case, we had to make a step loader that actually is a probe in order to get the bandwidth. Now, it is easy to transform between time and frequency. So you might say, well, I can do the step load response and then I can get the frequency because we learned how to do that using Fourier transforms. And if I have the frequency domain information, well, I can get the time domain because Laplace gave us that transformation. So thank you to both of you guys. You did a great job giving us both Fourier and Laplace, allowing us to transform bidirectionally between time and frequency. And so why do we want to do that? Well, one reason that we want to do that is, as I said, Qorvo needed to understand the performance of their power supply, which is unavailable inside a monolithic chip. All we can measure is the external response. We could measure impedance, which is relatively difficult to do on a 65 volt power supply. But even more so, when we measure impedance using a vector network analyzer, we're measuring small signal responses. And in an RF power amplifier, when it pulses, it's not really small signal. It goes basically from 0 to RF power in less than an RF cycle. And so that really looks like a much larger signal. So for that reason, we want to use large signal response. We actually used a software package that we haven't published yet at Picotest. It's called Sepia. We do hope to be bringing that to oscilloscopes soon. In fact, I'm giving a webinar in May on what the next 5 years of oscilloscopes looks like, and I'll be talking about Sepia there. In any case, what we did is we take this step load response, which gives us time domain, and from the time domain, we convert that into a equivalent SPICE model. a lumped element model, and that's done using the Fourier Laplace transforms bidirectionally. And of course, from that network, now we can synthesize what it is that the impedance versus frequency looks like. And so now on the left-hand side, we have the time domain plot. On the right-hand side, we have the frequency plot. And if I do a step load on our simple RLC model, you can see that almost perfectly overlays with our measured response. Now, this becomes complicated at this point because now we do have this impedance profile, but one of the things that Laplace taught us is that impedance has many different representations. For example, in a second order system, there are at least 3 transformations, one for an underdamped response, one for a critically damped response, and one for an overdamped response. So you can see I did all 3 of these responses on the right-hand side. They all give us very different time domain responses, and yet they all give us the same impedance. So there's this one-to-many relationship. One impedance gives us many time domain responses. In the other direction, it's much more complex. One time domain response doesn't give us many impedance responses. And so in order for us to get from one step load to the many possible responses, we need to get back to frequency domain first. In this case, the only thing we're changing is the width of the pulse of our transient. It gets a lot more complicated if the quality factor of the resonance increases. Now you can see the sharper Q and the taller peak, and now you can see that there are multiple responses and they're much larger. Again, only changing pulse width. And so we have this one-to-many relationship again. There's actually even more than 3 responses, and in my target impedance in Rogue Wave paper, I defined some of the others. But for example, a sine wave excitation and a square wave excitation are different. There are time relationships between the onset of the transient and the response. Some of them actually have a decaying representation, while others have an exponentially growing representation. And if you have more than one peak, of course, that's how you generate rogue waves, and that was the point of my target impedance in Rogue Wave paper. But now I think we've clearly shown this one-to-many relationship. Of course, our goal was to get the stability information out of this monolithic chip. And so using the step load, transforming to an RLC model, we can get to impedance. And now from impedance, we can use our NISM, which is built into the Bode 100. In fact, that's the only instrument it's natively built into, and that'll tell us that the stability is about 69 degrees. We can also compute the Bode plot. We can also do that inside the Bode 100 now, thanks to measurement equations. But we have this relationship that tells us that closed loop is equal to open loop over 1 plus t, where t is the loop gain vector. And solving for the loop gain vector, we get this simple equation, 1 minus impedance off divided by impedance on, and that'll give us the Bode plot. You'll notice those are quite close together. They're not perfect because one is a small signal computation, one is a large signal computation, and also the power supply we're measuring isn't precisely second order. There are actually multiple loops in that regulator. But you can say they are quite close. So if we can go back and forth and we can do frequency versus time and time versus frequency, then the question you might ask is, so why work in the frequency domain rather than the time domain, especially if we're comfortable doing step load responses and don't know much about vector network analysis or S parameters? Well, one is, as I showed, a singular impedance response provides many time domain responses. And so if we measure a time domain response, we don't actually get the family of possibilities. We only get the one case that we looked at. We would have to go back to frequency domain and then transform the many solutions in order to see them all. In frequency domain, we have lower noise measurements, and that allows us to get much higher dynamic range, and you'll see in a minute that that becomes really important. When we talk about dynamic range, the time domain has linear scales, both the X scale and also the Y scale. I'll be talking a little bit about that in my May webinar on oscilloscopes, but it really is important that scopes add log time and also log voltage in order to be able to accommodate these large dynamic responses if you hope to see them in the time domain. Vector network analyzers in the frequency domain are very easy to calibrate, and they're also very wideband. And oscilloscopes, that's not really quite true. In the webinar, I will be talking about de-embedding, which is built into some of the newer scopes, so they can actually do effective calibration to remove the effects of probes and fixtures. That's not really common yet, but I think in the next 5 years it probably will be. Frequency domain, since it does provide the one-to-many relationship, it makes it very easy for us to determine the worst-case stimulus. And in the case of multiple responses, it also tells us what the data pattern has to look like in order to get close to approximating a worst-case rogue wave. Finally, generating time domain stimulus can be really hard. You know, one of the most difficult things in our Corvo measurement was trying to figure out how to do a 65-volt 3-amp pulse with a 500 picosecond edge in a 1-inch probe. And that's not easy to do. It's not something that the average engineer is going to be comfortable with, and it can be quite expensive. So in a vector network analyzer, we don't actually have to worry about generating that stimulus, and in time domain we do. And most of the time we're measuring low impedance. That's not always true, but most of the time, at least in power, we're measuring low impedance. That means we're using something called the two-port shunt-through method. That can be really challenging, especially when you get down to really low measurements. With careful attention, you probably can get there. This is probably the lowest impedance measurement I've ever made. And I made this measurement directly with a Bode 100, measuring 20 microhms. And of course, just for correlation, because we have to measure something we know, I did actually put 7 amps of DC current through that resistor using one of the ports, and I measured the voltage on the other port at 140 microvolts. And so you can see 140 microvolts divided by 7 amps is 20 microhms. So we do know that's the right answer. Are people actually building power integrity buses at 20 microhms? The answer is no. I haven't seen one yet. But I can tell you that I have helped customers with 32 microhm buses, and that was actually the reason for doing this 20 microhm measurement, was just to make sure that we had reasonable margin for a measurement of 32 microhms. Getting there is a little bit difficult. If you look at the two-port shunt-through measurement, it's really quite simple. Engineers kind of struggle with the thought of it a little bit because we take 2 ports from a vector network analyzer and then we short them both on a dot, and that doesn't seem quite to make sense. You can see here I have one port of the VNA directly connected to our dot. In this case, I'm using a resistor, and in the other case, I'm showing a ground loop isolator. And in this plot, I'm showing how that measurement is impacted by different isolators. You can see the dramatic difference, especially below a kilohertz. Without any isolator at all, you can see up to about a megahertz, but with an isolator, below about a kilohertz. One of the reasons that it's really important for us to measure our own capacitors is because often data doesn't go low enough in frequency. I'll talk a little bit about that a little bit later. If we look at the measurement, it's really simple, right? Inside the vector network analyzer, for simplicity's sake, I put a voltage source that is 2 volts. And I did that because the source has a 50 ohm source impedance and port 2 has a 50 ohm load impedance. And if I were to connect those two, port 2 would measure 1 volt. That would be unity gain, and that would be actually our calibration point. If I connect the dot between them, as I'm showing it here, a 1 milliohm resistor, for example, now we can see that the correct answer is 40 microvolts. Why do we need such large dynamic range? Well, you can see here that this measurement is a minus 88 dB measurement. So we need at least 88 dB dynamic range plus noise margin. And here are the equations if you're interested in looking at how it is that that's impacted by S parameters. But of course, that is the right answer. Now it gets a little bit complicated as soon as we add a cable because the cables themselves have resistance. Here in this case, I just drew 2 cables that each have shield resistance of 10 milliohms. So that would be 2 equal length cables. And you'll notice that at the front panel of the vector network analyzer, both shields are connected to, let's call it RF ground, the front panel of the VNA. And at the other end, they're both connected at the bottom of the dot. And so now if we look at what it is that we see at port 2, we actually see the parallel equivalent of the two shield resistances in series with the dot. And now we're not getting 40 microvolts anymore. We're getting 240 microvolts. We're not getting minus 87 dB. We're getting minus 72. And if we do the impedance transformation, that says 6 milliohms. Why 6 milliohms? Because we've got two 10 milliohm shields in parallel, which is 5 milliohms, plus the 1 milliohm dot. And that says that we have this measurement error now that's 500%. In order to fix that, we need to isolate the ground loop from the vector network analyzer of at least one of those channels. Here I installed a DC transformer. Of course, there isn't really such a thing as a DC transformer, but this is a DC transformer. There is no limiting inductance. Now we've isolated the two ports, and you can see that now the voltage went up quite a bit from 240 microvolts to 440 microvolts. But if we look at the dot, what we see at port 2, that's back down to 40 microvolts, which is approximately the right answer. That's a function of the common mode rejection of the isolator, which I set to 0.999. And if we do the calculations here, you'll see now we're within 1% error. If we look at what that looks like in equations, I actually published these equations in 2018 as part of an EDICON University presentation on measuring below 100 microhms. And here are all of the equations that relate shield resistances to the isolator and even the inductance of the isolator and at what frequency the measurements become valid and so on and so forth. And so that's the reason that we see these low frequency errors. And of course, if we measure them, there is the measurement with different isolators. Using a solid state isolator, we get common mode rejection all the way down to DC. And so we get a valid measurement all the way down to 1 hertz. Using a transformer isolator, well, we don't, but we get valid measurements up, down to about 1 kilohertz or so. And without an isolator, we don't get good measurements up to about 2 megahertz. A question I often get is, why is it that at 2 megahertz it becomes okay? And the reason is that eventually there is enough coupling in the cable that the cable becomes the isolation transformer. And of course, the cable doesn't have great coupling, which is the reason that it's at high frequency. Now, of course, we need to connect these cables to the dot, and that's where it gets a little bit complicated. And that's really the major focus of this paper is how is it that we probe it, and in probing it, how do we impact the measurement? There are really 5 options we have. One is soldered down coaxial pigtails. We have others, RF connectors, probe points, browser probes, and microprobes, and I'll talk about all of them in detail. But here you can see 2 soldered down options. One on the left, you can see that's a rigid coax. The rigid coax is soldered to a capacitor. And you can see there's actually 2 of those cables, they're both soldered. Of course, there is some lead length between those rigid coax cables and the capacitors, and those lead lengths are inductive, and that will influence the measurement unless we can de-embed them. On the upper right-hand side, I wanted to show an older measurement. This shows off my soldering skills. I'm very well known for my soldering, and this is actually measuring 2-port impedance of a motherboard. And you can see how I just slathered some solder on the capacitors and laid down some RG58 coax. I have worked on my technique a little bit. It's gotten a little bit better. You can see on the bottom right, I took 2 rigid coax cables and I managed to solder them very close to an output capacitor with very short leads. And that provides a much better solution and also much more mechanically robust, since I also have the shields soldered to a turret so they don't break off so easy. One of the issues with soldering these pigtails is that they do tend to rip parts off the printed circuit board, so it is often destructive. RF connectors are a really great way to make measurements. Sometimes we can add those ourselves. Here on the left, you can see I just scraped off solder mask in order to be able to solder SMA connectors to the planes, and that actually worked out reasonably well. Now, of course, we don't have a lot of choices about where it is that we make our connection points. And when we do our EM simulation modeling, it'll be important that we locate the ports at the same point we located our measurement ports. Some of the newer devices, in particular the GaN devices, are including RF connectors for the purposes of making these measurements. Qorvo did include SMPM connectors on their board to allow us good access to the measurements. Unfortunately, not a lot of companies do it, partly because it takes up a lot of real estate, and partly because these connectors, at least good ones, tend to get quite expensive. We can use headers. There are a lot of different header types to choose from. Load Slammer uses a very large Semtech connector. It's a many pin connector, and you use all of the pins on one side as power and all of the pins on the other side as ground. They split them up in two parts so that they get a full wire measurement. So half of each side is one signal. So there is a left and a right signal and a left and a right ground, and that gives us the 4-point connection. That takes up a lot of real estate. And of course, the header itself is relatively tall. It becomes extremely difficult to try to de-embed the header, but it's possible. There are other types, like Milmax makes these headers that I'm showing in the upper right, and that'll provide connections. We really need 4 points to measure one impedance. One signal, one ground for the source, one signal, one ground for the receiver. So 4 wires total. There are also this particular one is popular in the bottom right, thingamafob, and that provides guide pins and also connection pins in order to make connections for the measurement. Again, it becomes a little bit not well adapted, and partly because, again, they're expensive, but also they take quite a bit of real estate, and it doesn't actually let us get very close to the points that we want to measure. Using test points, one of the things I did want to highlight is it's not necessary for the test points to be large. We can put test points on a printed circuit board that are really small. And to prove that, we made a bunch of little demo boards. We tend to give these out at trade shows and stuff. But we made a through connection so that we can do our calibration on the left side. We did a short pad on the right side so we can measure a short. And we put a 1 milliohm resistor in the middle. You can see this is just a whole panel of these test boards. On the back side, we have 4 printed circuit board pads. Those connect to the DUT through 4 vias in the printed circuit board. So 1 via for each of those pads goes to the DUT, and that gives us 4 connections. These pads, they're very small, but they're still much larger than they would need to be. We made those pads large enough so that it can fit any one of the heads in our 2-port impedance probe, and so we can make Kelvin connections through those pads. So with a little bit of forethought, we can actually add tiny little printed circuit board pads for the purpose of making these measurements. And if you want to keep them really small, well, you can limit those pads to a 402 size probe. When we actually make measurements with probes, we can actually do that using one of 2 choices. One choice is to use 2 1-port probes, each one providing 2 of the contacts. Another option is to use a 4-point Kelvin probe like our P2102 that does 2-port impedance all in one head. There are pros and cons to both sides, and there's nothing that's perfect. 2 1-port probes, well, you can see that they still do have spring pins, so there still is a little bit of tip inductance, but those probes typically are above 7 gigahertz. So, we don't really have a lot of problems unless we want to measure into the multi-gigahertz. That allows us some flexibility into where it is that we place the probes, and that's a double-edged sword. One is that it allows us to minimize coupling by moving far apart. But if we move them too far apart, well, then we didn't actually measure self-impedance. Then we measured something called transfer impedance, which is a little bit different. It also does give us the ability to measure impedance from both sides of the board, which minimizes coupling. We can't do that with a 2-port probe. A 2-port probe is really simple, and so we like it because of that. It makes all of the connections for us in one simple point, and we can do it on almost any component pad or even in an individual component. But it gets a little bit complex again. So here is a simple fixture that my daughter printed for me so I could take 2 1-port probe circuit boards and just change the relative angle between them. And so there are different slots on the board that have different angles for those probes. And if we measure the short excess inductance, you can see that on the left. And so the excess inductance is very significantly dependent on the relative angle of the two probes. So that is one of the complexities of using two one-port probes, is we really do need to fix the angles of the two probes relative to each other. And of course, as we move them further apart, it'll also have an impact on the measurement. And if we make them orthogonal, which will minimize coupling, that'll also have an impact on the measurement. So one thing that you can say about the two-port probe is that having the probes very close together does mean that there's coupling, but the coupling is very well fixed. It's not variable. And because it's fixed, it becomes possible to calibrate that out. We can do a little bit better using microprobes. Microprobes are much, much smaller. The pins are extremely tiny. In fact, you generally need a microscope to see them. They don't have any spring pins, so the placement of the probe is extremely sensitive. You need to get just the right force on the pin. It's extremely fragile, so if you use too much force, you'll break it. The pitch tends to be very, very small. You can see that they did fix the angle by the positioner. So we do fix the relative angle of the probes, but in calibration, it is important that we get them the right distance apart. And that does also require a substrate calibrator, which I'm showing on the right. There's not really a problem in using a substrate calibrator. They're extremely accurate, but they're also very expensive. And the calibration is a specific point on the pad. And so you'll see that there are instructions about where it is that the two pins have to contact the pad and how to place Mylar tape over the calibration structure so that you can make dents in the tape to make sure that you don't over compensate the pressure. So we can just dent the tape, and then we can remove the tape and repeat the placement of the probe using a finite number of fixed turns of the positioner. So if you need to make higher frequency measurements or you really need to minimize the coupling, microprobes are a good way to go, but it also does require positioners, microscopes, and a little bit of other complexity. So if we look at the different options, here they are, and I kind of sorted these by the different things that they influence. So one is just the ease of the connection. One is how repeatable is it? Soldered pigtails, for example, it's not very repeatable unless we can make sure that we make the bend angles of the center pin and the exact length of the center pin the same every time. Not only that, but also we need to try to make sure that we contact it at the same height on the capacitor or the same place on the pads every time we solder it. Cost, what does the relative cost look like? What is the accuracy of the measurement? How is the bandwidth limited? And what is the shield resistance? Those are the criteria that most significantly import the measurement. And you can see that, each one has its ups and downs. So for example, RF connectors have excellent repeatability. Shield resistance isn't really great, and they're not necessarily low cost. And so we're always making trade-offs in what it is that we're trying to accomplish and how it is that we accomplish it using the variety of approaches that are available to us. Now, of course, one of the things that gets into the accuracy is how well we can calibrate our probe. Vector network analyzers do tend to make simple work of calibration, but that's not as straightforward as it sounds. One of the greatest features of the Bode 100 is that it allows us to remove two-port fixtures using two-port short, open, and load. Most vector network analyzers don't allow us to do that. That allows us to account for many of the errors that get associated with the two-port measurement, including the probes and where it is that the fixture pins land and so on and so forth. And in our own tests here, even using our probes, we've been able to replicate excess inductance to about 60 picohenries. So that means a variability of about 60 picohenries in our measurements over the course of a very large number of measurements. One question that I do get is that why don't we just calibrate out that low frequency error And so before you guys ask it, I'll try to answer it for you. The error is really large. And so while we can see the shield resistance in the measurement, and we can remove it in calibration, we haven't done anything about the sensitivity of the measurement. So let's take our example where we had 5 milliohms of shield resistance in series with our 1 milliohm resistor. So we can subtract 5 milliohms. The calibration will do that when we try to make the measurement. But it still has a sensitivity of 1. So if it becomes 5.1 milliohms, well, we've already got 100 microhm error, which is 10% of our 1 milliohm measurement, because we haven't done anything to attenuate the error before we subtracted it. So the reason that we want to solve the ground loop first is to reduce the sensitivity of the measurement before we calibrate it. So the trick really is calibration. And of course, the lower impedance we go, the more important it is to do our calibration. For higher impedance, you can often get away with just doing a through calibration. If you want to get ESL of a capacitor right or power plane inductance right, it really does become important to do short, open, and load two-port fixture removal, which is this one on the right-hand side. Calibration does allow us to make really precise measurements in a very low impedance. Here's how we measured 20 microhms. One of the things I highlighted in this university paper that I did this for is that we need to get incredible dynamic range. I showed that at 1 milliohm, we needed 87 dB. That means that at 100 microhms, we need 107 dB. And that means at 10 microhms, we need 127 dB plus the noise floor. So we're looking at somewhere around 140 dB dynamic range to measure 20 microhms accurately. Achieving that can be really difficult, but one of the things that I highlighted in the paper is there's only one way for us to improve the signal to noise ratio in this measurement. We can't put a preamplifier on the right side of the measurement on the receiver. That'll just amplify the noise that's on the board. So everything gets elevated, both the signal and the noise. It doesn't make any improvement in the signal to noise. The only way to improve signal to noise is to put a source power amplifier on the output. And so we use the BAMP12 for this measurement. That increases the source level quite a bit. That improves the dynamic range, allows us to make better measurements. We put the coaxial isolator first to improve the measurement, and then we do the calibration, and now we can do an accurate measurement of 20 microhms. If we wanted to summarize what this means, there are several connectivity options that we have. Different circumstances are going to warrant different selections. One of the things that's common to all of them is how it is that we actually make connectivity to the DUT. One of the things that is important is that we always contact the DUT at 4 points. So for example, in this measurement setup on the left, we connected the two connectors together first, and then we put these very short traces to the DUT. That's not a 4-wire measurement, it's only a 2-wire measurement, and it is going to add quite a bit of inductance. We really do need 4-point connection, so you can see how I did that on the right. We want to try to make sure that we do that with our 4-point probes and any 4-wire Kelvin measurements that we make. We want to try to make sure that we make this at 4 points. We also want to try to make sure that it's at the right 4 points. Measuring a capacitor is not the same as measuring a circuit board plane. And one of the things that we need to be careful about when we measure capacitors, and I think Frank mentioned it, but maybe not all that clearly, is that we typically use models for capacitors because at low frequencies, they look like a short. It's not entirely true, but the measurement makes it true. If we can measure a capacitor over some frequency range and get the S parameters, it will give us the impedance over that range. For most RF vector network analyzers, those are going to start somewhere around 9 kilohertz, or some start at 100 kilohertz or even 300 kilohertz. Whatever the impedance is at that point is going to become the truncation in the S parameter. Everything below that is going to use that impedance. So if I measure a large capacitor, and I measured at 9 kilohertz, it's going to have a very low impedance. The S parameter in the simulator is going to take that impedance as being valid for everything from 9 kilohertz and lower. That includes DC. So very often, if you use an S parameter model in a simulator, you're going to see that you have hundreds of amps on the VRMs, and that's why the current is flowing through those. So we want to try to make sure that we make our measurements at really low frequencies if we want to make sure that we're not going to create those DC solutions. So the lower we can measure in frequency, the better. Also, Frank mentioned that when we measure capacitors, they have tolerances. So one of the reasons we measure capacitors here is that we do those correlations. We don't want to make allowances for those tolerances. We want to know the actual value of the capacitor that we measured. And so even when we have models, we typically want to make these measurements for the reason of getting that data. And yet another point is that the question got asked, do these models include DC bias? And the answer is no, they don't. Even when they do, it would be at a fixed bias. They also don't include AC bias, and the AC bias is often as important as the DC bias. Vendor models are typically measured at either 500 millivolts or 1 volt of AC signal. When we measure power distribution network, when we measure with a vector network analyzer, we're using microvolts or millivolts. And the capacitance is very different at microvolts or millivolts than it is at 1 volt. In fact, just today, about 3 hours from now, I'm working on a DesignCon panel discussion. And the session that I have is called "Are Vendor Models Always Wrong?" And the answer is they are, for different reasons. For example, Murata, they do define how it is that they make their models very clearly. And they made their models at pads of the printed circuit board using their pad patterns. That becomes really important to understand, because if we get the capacitor measurement or model from Murata, and then we place that on the pads in an EM simulator like, Marcus showed ANSYS, we're going to add the extensions for the pads and vias that were included in Murata's measurement, but those are also included on the printed circuit board EM simulator, so they're going to be counted twice. I did do a paper on that last year at EDICon called "The Partial Inductance of Capacitors," and I showed a lot of different vendor models and why each one of them is wrong. But for example, Murata showed their 805 1 microfarad capacitor to be 350 picohenries of ESL. AVX showed their similar capacitor to be almost 800 picohenries of ESL, and we measured both of them. They were both exactly the same at 140 picohenries. What does become important when we place these into a EM simulator is that we got to get the port placements in the right place. And that means that we need to do the calibration at the point that we're going to measure, which is typically the pad to pad distance on the capacitor, not on the printed circuit board. So we need to calibrate out that physical length in our short calibration, and then we need to measure on those termination pads. When we connect to the printed circuit board, then we need to make sure that the pad locations or the port locations from our measurement align with the port location on the board. That's one of the more common errors that we see in correlating PDNs. Calibration is really tricky. You need to make sure that you do it appropriately. You need to make sure that you do it accurately. In the case of measuring low impedance, very low impedance, that also means that you have to make sure that you understand the coupling of the probes and get it fixed so that it's not a variation. My biggest tip is always measure something you know and make sure that it's of a similar magnitude that you want to measure. So, for example, when Mayo Clinic needed to measure 32 microhms, we could measure a milliohm and say, okay, so we now got a valid setup, and then measure the 30 microhms. But those aren't the same magnitude. So that doesn't prove that we can accurately measure 30 microhms. It would only prove that we could accurately measure 30 milliohms. So we wanted to overperform the measurement, but the same order of magnitude, and that was the reason that we measured 20 microhms. In that same series, we also did measure 33 microhms, and it was very difficult to actually make the resistors. We made those resistors here, and so we kind of got what we got, and we tried to adjust them to the little bit that we could using grinders and uneven solder. The cable shield and the ground pin resistance is really significant, and I didn't talk about that before, but I showed the ground resistance error and how that gets into the low frequency measurement. So we have these shields, and the shield resistance becomes part of the error that we need to calibrate out. For that reason, we want to do two things in our measurement. One is that we want to reduce the shield resistance as low as we possibly can. That's the reason that Picotest made PDN cable, is we needed cables that had lower shield resistance than a typical SI cable. We also needed to maximize the common mode rejection of the isolator. That's the reason that we went from our J2102A isolator to the J2102B isolator. But now what happens when we add spring pins? The spring pins are also resistive. And of course, they have variable length depending on the spring compression. And that adds a small variance in inductance and also a variance in resistance. So one of the things that you want to be careful of when you use probes is you want to try to make sure that you calibrate and measure using the same compression. And that's a little bit tricky. You want to fully compress the probe so that you get to the minimum resistance, which is still going to be higher than the ground shield resistance of a cable by itself. So we are sacrificing that a little bit for using a probe, but we'll minimize that if we fully compress the pin. Same thing with the inductance. On the other hand, if you push too hard, these spring pins are very fragile, especially in our smaller probes. It's a 20 mil diameter pin, and that's got actually spring networks and all kinds of stuff inside that 20 mil pin. So it's very tiny. It's relatively simple to break those pins. So we want to use enough pressure to fully compress it and not enough pressure to break it. Anyway, I hope I gave you a pretty good overview of what it means to make these impedance measurements, why we want to make them, how to make them accurately, and how it is that they're impacted by probes. If you're interested in finding out more about these measurements or actually seeing the online demos, they're available on our Picotest website. You can join our LinkedIn group, Power Integrity for Distributed Systems, and you can visit Picotest.com or omicronlab.com to get more information about PDN impedance in particular, measuring impedance, and also about our non-invasive stability margin measurement, NISM. Anyway, I hope you found this interesting, and I hope that it helps you make more accurate impedance measurements. And it was really my pleasure to share this with you.